Hello, everyone. I'm Jia.
And I'm Steven.
We work at Meta building Firefly, a type checker, and an IDE tool. Our team has been working with other Python teams at Meta that wants to adopt types for the past few years. So we've seen firsthand where people hit walls. This talk is for anyone else who's had that kind of experience. We want to be honest about the type system's limitation, where the type system generally struggles, and discuss what to do about it. But briefly, why do we care so much about adding types in the first place? Types catches bug before your users do. They are documentations that the machine can verify. They make refactoring safe, rename a parameter, and your type checker lights up every call site. And they power the IDE features you rely on every day: autocomplete, go to definitions, etc. And typing isn't a niche thing anymore. A recent survey found out that 89% of the developers who are aware of typing use it regularly. We've seen a generation of libraries built type first: Pydantic, FastAPI, Typer, and others. Even legacy holdout like NumPy is catching up. It went from 33% to 88% type completeness in a single focused push. The momentum is real. With all that momentum, we'd expect that adding types would be straightforward, and for some code it is. But responses from the same survey we showed earlier suggest that for a lot of code, the picture looks different. People pointed out that type system has limited expressiveness. People discovered certain kinds of code are painful to annotate. And certain libraries exist without any typing support at all. Many of those are perfectly good Python that predates typing and don't translate cleanly into the post-typing world. Not because the code is broken, it runs great. The type system just wasn't built for this flavor of Python. And there's the gap.
So we'd next like to talk about 4 common situations we've come across where you might have perfectly working but untyped Python code that really doesn't fit the semantics of statically typed Python very well, because the languages have different rules. Statically typed Python is more restrictive. And these are cases we've run across. We'll talk a little bit about tactical fixes, and then later we'll talk about how you might approach it if you're running into a lot of these problems. The first example we want to talk about is when you're mixing together different types of data in some sort of a container in a way that the static type system may not like. We'll start with one of the most common things that Python developers frequently do as an early project, which is just pull in data from some API and then try to do something cool with it. Maybe we're plotting it, maybe we're analyzing it. When we do this, we have an HTTP request object, an HTTP response object, but as soon as we try to deserialize the data, it's all sitting in a string. So the type stubs are going to say we get any out. And if we don't take any specific action, any operation we take on that data, indexing into it, we're going to keep getting any. Any, for anyone who's not terribly familiar, it just means to the static type system, we don't know anything about this type, don't raise any errors, you really can't provide any IDE support. And so you're not going to be able to catch if there's a typo somewhere in your code and you're trying to use a field that isn't there. You won't be able to get something like autocomplete or tooltips that we would like to use type information to inform. And you may find that you're passing data to the rest of your application in a way that blows up downstream, and you get pretty difficult to debug errors much later in the program. This particular example is actually possible to type using typedict, which is a special class that really declares the type of what's inside of a dictionary if it has fixed keys with known types. So this example, we can type it as list movie, and we actually get all of those IDE benefits. There's a little bit of a gap here still, though, because if we take this approach, the type checker's taking on faith that this response really does have a list movie. And if we misunderstood the API, or if the API changes on us, we'll still get very strange errors in downstream code that we thought was well typed. It is possible to do better with a library like Pydantic, where you might actually use classes to represent the data and have an explicit step that validates so that you always get runtime errors at that boundary if the API changes on you. The problem's not restricted to just dicts, though. For example, a lot of untyped Python code will use lists as a container to mix different data types where the program is somehow aware of the structure of what's in the list. So here, for example, we have a list that we know has a string and then an int, and maybe our program's depending on it. I came across a very similar example in the VGG computer vision model, for example, where it was dealing with neural net layers in exactly this sort of way. If the code looks like this, we actually can really easily move it to be statically typed, because the tuple type is how the static type system represents a sequence of different values where we remember what each of the types are for later use. But the problem is, in a lot of these code bases, we might actually be building up that list over time as a function executes with append operations, and a tuple has to be constructed all at once. So this could be a problem where you might have to do non-trivial refactors to adopt static types. Data frames, of course, are a little bit similar. If we read in data to a data frame, we have a very well-typed object at some level. We understand all the methods on data frames. Pandas has pretty good type stubs. But the analysis probably depends on the columns, and Pandas has no idea what the columns are. So once again, we'll be unable to get autocomplete. We can't get typo detection. And when we actually work with the columns, we will understand that they are series objects, but the actual analysis probably depends on data type aware transformations because, for example, a column of strings allows you to do different things than numeric columns. And this effectively means a lot of code working with data frames is mostly untyped. There have been experiments in the library ecosystem with how to do better. For example, the static frame library tries to use typevar tuple to improve this situation. Nothing has seen really wide adoption so far. Another case that we run across really frequently where untyped code can be very difficult to statically type is where the logic is just dynamic at the level of kind of how values and variables behave. There is very good support in the Python type system for some simple cases of this. Here we have what's called narrowing, and every type checker will understand that although value could be a string or an int, once we hit the isInstance gate, it's going to be an int, it's safe to add 1. But narrowing can be more complicated than that. It's pretty common in older libraries that deal with different kinds of types to see flags defined, maybe at the top of a function or maybe even in the parameters, that somehow knows something about the types and then reuse that and want to get narrowing in blocks where we're injecting conditional logic throughout the function. And support for this is mixed. The newer type checkers I've looked at largely do support this, but not all do. Firefly and TY, for example, do support this. In addition, there are cases where things will typically work well at runtime, but no type checker will allow it. Like if we try to narrow what's inside of a container, for reasons I don't want to get into, no type checker will allow this because it's not really safe at the level of how the type system works. And so if we have code like this, it's going to be very difficult to apply static typing without making major changes. We can also get dynamism not through the control flow of a function, but through how instances evolve as our program runs. A very, very common case we've run into where type checkers will throw a lot of errors is if the constructor to a class doesn't fully initialize it, and then there are later methods that complete the initialization, where by initialization I typically mean that the fields of the class are not all populated in the constructor. So here, we have a connection class that at construction knows where it would connect, but it hasn't connected. And the socket attribute isn't defined until we hit connect. This can be hard to type, and we'll have to choose between a more convenient but less safe option where we pretend socket is always defined, and then you might get errors the type checker can't find if you try to use a send method call before a connect call. Or we would have to say, oh, socket starts as none, and then we're going to have to be narrowing throughout our code base, which can be a pretty invasive change. In typed Python, we would typically prefer to use two separate classes to represent either where we want to connect or the actual connection, but that can be a big refactor. Meta classes are another form of dynamism, and class decorators can behave similarly, where the actual class definition that type checkers want to analyze isn't describing how the class will really behave, because either the meta class or maybe the decorator changes behavior. Here we have a Django model, and it looks like name and age are these special field objects. But at runtime, on an instance of user, we're just going to get a string and an int. And what's happening is that the Django meta class logic is wiring up ways of connecting to a database and things like that. Some kinds of meta classes are supported through the data class transform PEP, which was intended to allow libraries like Pydantic and adders that behave a lot like data classes.dataclass to be understood by type checkers. But other meta classes either need built-in support or they just won't be understood by type checkers. For example, MyPy can understand this with the Django plugin, and Firefly has built support for this sort of thing, but it varies across type checkers. Duck typing is kind of the last category that we think you can run into easily in an untyped Python program. This is the behavior where the Python runtime doesn't care what a type is in almost all cases. It cares what operations are defined. If we have a library that writes out a report and all it really relies on is a write method on the output, then it doesn't matter what we pass in as long as it has a write method that can accept a string. The code will run, and then its actual behavior will depend on what we passed in, which will depend on what we wanted to do. So we can pass in an open file object, but we could also use a string IO to collect the report into a string, maybe because we want to display it on a web server or in unit tests. And we could also create our own network stream if we needed to send the report to a different computer. If we try to add types using the most common approach in the type system, which is nominal typing, we're going to hit a wall here. Because io.textio.base, that is where files get the write method. But if we try to use that, string IO doesn't inherit from that class, and neither does my network stream. There is a workaround. As long as we control the report function, we can use a protocol which was added in PEP 544 and represents a duck type. Here, the writer protocol, which is a simplified version of what's actually in io.writer in the standard library, says, I am a valid writer if I have a write method that has what we need here. And with this, all of our examples work. There are a few usability issues here. For example, if we have a lot of protocols in a library, we might have functions that rely on different combinations of those protocols. And it's not a problem if we have just a few of them, but you can imagine with many protocols in different combinations, it can get annoying to write out all the protocols. There's a bigger problem, though, which is that we use Python largely because of the library ecosystem. There are so many libraries that are useful. And that means our save report function in a real example very likely is not our code. It's something we pulled in from PyPI. And if the library author didn't anticipate that we might want to use duck typing with it, it's pretty likely that they may have actually written a concrete class type. And so if we have examples that aren't inheriting from that type, type checkers will reject the code, even though it works at runtime. At this point, we actually kind of run into a wall, and we might be able to do an end run. For example, if type checking blocks are one way of kind of lying to the type checker about what's going on if you really need this. But that comes with trade-offs, because now the type checker is not actually validating your code. So you'd better be very confident that what you wrote is correct. These kinds of things do happen in reality. I think many of us have worked with unit test mocks, which duck type everything. There's no real way to express this in the type system, so the way we do it is we have it inherit from any. But that means that effectively the code is untyped in unit tests. There are other examples. For example, CuPy is a library that implements most of the NumPy API, but using GPU accelerated arrays. And if you try to use a library like a stats library or a physics library written for NumPy with CuPy arrays, you are potentially running into these kinds of duck typing problems. And similarly, it can happen under the hood. Like PyTorch compile relies on fake tensors to trace what's going on in order to optimize an ML model.
Okay, now, knowing all those hard-to-type patterns, what should we do? Stephen already talked about ways to work around some of those issues. But if the patterns are really pervasive in the code base, reaching for those workarounds repeatedly can get tedious or undesirable. So instead of immediately tackling the problem of how to type the code directly, let's take a step back and ask a different question. Should we actually add type to the code in the first place? We already said in the beginning that types are valuable, but that doesn't mean that every piece of code benefits equally. When the code resists typing, adding types to it is no longer free. So the question becomes, for this specific code, is it worth the cost? That's the cost-benefit question. Let's start with the benefit side. If your code is fast-changing and business-critical, say a serving layer or a core SDK, types pays for themselves pretty quickly. Having type checking as a validation layer catches the bug before they hit production and allow you to move fast without worrying about hidden breakages inside your code base. When your library API are dependent on by hundreds and thousands of developers downstream, people also get the benefit of strongly typed APIs via better IDE support, as well as their own type checking, so that they could prevent your APIs from being used in inconsistent ways. But if the code is battle tested, rarely changes, and has a solid test coverages, the marginal value of adding types is much lower. Same goes for exploratory work. Notebooks, prototypes, research models, those demands more speed and flexibility and less setup. Now the cost side. The dynamic pattern we just talked about, heterogeneous collections, dynamic attributes, and others, makes typing genuinely expensive. Adding types to that kind of code base means fighting the code's entire design. Same goes for large legacy code bases with decades of organic growth and intricate undocumented component interactions. Typing those code bases is more of an archaeological expedition. On the flip side, if your code mostly sticks to straightforward functions, data classes, and explicit data flow, or if you're starting from scratch working on greenfield projects without much legacy to deal with, then adding types become relatively cheap. Combining the benefit side and the cost side, this gives us a 2x2. Low cost with high benefit, low cost with low benefit, high cost with high benefit, and high cost with low benefit. Let's look at the strategies for each. When the cost is low, our recommendation is simple, just type it. Regardless of whether the benefit is high or low, if it's cheap to add types, there's little reason not to. Here's an example. Before, a function returned a list with multiple elements, no types, no structures. The caller has to remember what's at index 0, 1, or 2. Now, after adding the type, it's obvious what you're getting back. The IDE helps you, and types get caught immediately. This kind of refactoring has gotten drastically cheaper with AI coding agents these days. Our experience is that AI tends to work decently well on this kind of tedious rewrite task, turning untyped code into typed code fairly autonomously. That shifts the cost curve. More code fall into this bucket than you might have expected. In fact, we ran a study on a large internal code base at Meta and find out that AI-based code mods can fix over 70% of pre-existing type errors in the code base automatically. Granted, the code base already has high type coverage, and not all AI-generated fixes are of the same quality, but the direction is clear. Now the unfortunate corner, high cost, low benefit. Our recommendation is don't bother with type perhaps, stay dynamic. And I don't just mean it's not worth the effort. I mean, applying types to code that's never designed for them without rewrite can sometimes even make things worse. Here's an example function that's supposed to handle multiple legacy data format: strings, bytes, dicts, list, custom objects. If we were to start the project today, we would probably be mindful of the serialization format and reach for good three-party libraries to handle the messy deserialization logic. But remember, we're talking about the high cost, low benefit category. And in such scenarios, we're more likely dealing with battle-tested legacy code where changing the code or adding more dependencies is often not a good option. Down below, you can see the result of adding type annotation to it, and look at what it does to readability. It makes things harder to read, and we're still not getting much out of the annotation since the return is still a type unsafe JSON blob. And readability isn't the only failure mode. Refactoring stable code just to please the type checker risks regression. And every hour you spend on it is an hour you didn't spend on shipping something your user need. Types are means, not a goal. If the cost is high and benefit is low, don't bother can be a good option. But what about the case when the cost is high and the benefit is high? That's where things get interesting. And we need to think harder and be smarter about where we want to prioritize our effort. Let's look at a concrete example. This is an event dispatch system. We have a registry, a dict that maps event type strings to their handler functions. We have this register function here is a nice decorator that can be used to add handlers to this registry, just like this. We have register 2 handlers here to process purchase event and refund event. And this process event function does the dispatch. It takes the event JSON, looks up the right handlers by event type, call it with the payload, and notify the source with the result. It's simple, readable, and it works, but it's hard to make type safe. What's the type of the registry here? It maps from string to callable, yes, but there's no single callable type to use here without involving any type, because the handlers don't necessarily share the same return type. This is another textbook example of the heterogeneous container pattern Stephen mentioned earlier, which is pretty resistant to static typing. So what can we do here? One option we could do is to type it to completely refactor the code to make it fully type safe. Don't worry, you don't need to read any of the code on the slide. It's just shown here to give you a sense of the scale of this refactor. What we basically did was to define typed event classes for every kind of event, purchase event, refund event, each with its own payload shape and return type. Every handler's signature now changes, and we no longer have the nice decorator setup we had before. This can be done, and yes, it's 100% type safe, but it's also fundamentally different architecture from where we started with, and therefore is a substantial rewrite with real regression risk. Here is another approach that I call wrap the boundary. Instead of rewriting the core, we leave the untyped process event completely untouched. We add a typed wrapper function that takes a typed incoming event structure and return another structure called typed event result. And the body of the wrapper massages the data and forward them to and from the untyped dispatcher. And here's the definition of the incoming and outgoing data structure. I use Pydantic here just for data validation and serialization. Here, this version is less type safe than the full rewrite. In the fully typed version, downstream code knows exactly what fields are available for which kind of event. But in our version, payload and the input and the data and the output are both opaque. Downstream consumers get typed access to some structured information about shared metadata, but they need a runtime check to access handler-specific field. That's the cost of this approach. We lose some type precision on the per handler input and output, but we made 0 changes to pre-existing code. 0 risk of functionality regression here. 1 wrapper function, 2 Pydantic models, and our client code now has a typed interface to work with. What we just built is this pattern. We leave the dynamic code alone, untouched, unchanged. We build type boundaries around it, validating what goes in, structuring what comes out. Downstream code only interact with the core through the typed interface. It never touches the dynamic core directly. We get partial type safety, paying partial cost. So the bottom line, when the cost of typing is high and benefit is also high, it's probably smarter to avoid optimizing immediately for full type coverage heads-on because of the high cost. Instead, we want to aim at maximal typing benefit per unit of effort. Establish some boundaries around components. Get some types around the boundaries, reap some short-term benefit, and come back to full typing-oriented refactor later if desirable in the long term.
We've talked a lot about working with statically typed Python as it exists today. But something we wanted to touch on as well is that the type system itself is changing over time. It's a community-driven effort, and it evolves to meet the needs that we identify when we find a solution that we think is a good solution for the users. Types are here to help. PEP 484 defined the static type system, but we've had many PEPs, we've highlighted a few here, that are based on extending the type system to model more dynamic logic than it originally did. For example, we've already talked about the protocols PEP, which was PEP 544 in 2017, added a few years after the original introduction of static typing. And every one of these PEPs started with someone saying, I have code, I can't type it using the current static type system. What can we do to make things better? The community is always looking for how we can support Python users better. There are trade-offs because the type system is already complex, but we're actively looking at things like improving narrowing. As we just touched, different type checkers have been improving the kinds of conditions where they can track narrowing based on what we see in real code. There are discussions about maybe adding intersection types, which would have a number of benefits, one of which is that verbose protocol example where we try to combine different protocols in a heavily duck-typed code base, and it's difficult. It would be much easier with intersections. And as we already touched on, there have been libraries exploring better typed interfaces to data frames for things like statistical analysis. You can help. Most of the typing discussions happen on the typing discourse. There's a typing channel, and this is where people bring up issues where they're wondering if the static type system can already handle a problem or floating ideas for what we could do better. And the typing repository under the Python GitHub organization is where the typing specification lives, and you can see how it's been evolving over time. This wraps up our talk. Just to recap what we've discussed, untyped Python is a language with different semantics from typed Python. The semantics of typed Python are more restrictive, and it can be difficult to migrate an existing code base to using type annotations. And we've touched on a number of strategies, both tactical and more around module boundaries that you can use when trying to do this migration, as well as how to get involved in the typing community. Jia and I both work on the Firefly type checker, which is one of many type checkers that are trying to meet users' needs better. And we just reached V1 release, which is really saying we believe this is now stable and reliable. If you'd like to learn more, go to firefly.org. And that concludes our talk. And if you have longer questions, you can meet us out in the hall. We're happy to take more questions.
I was wondering, you mentioned like 70% success rate in converting from untyped to typed. I guess what happens, or do you see engineers wanting to do like Claude and use frontier models and say convert from untyped to typed? And how successful is that? How much hallucination happens? And does your library sort of help that, I guess?
What we have done that we can actually get numbers on are experiments where we synthetically looked at some workflows of resolving type errors, which are often gaps in the type system, and I think are a little bit emblematic. We certainly have heard of people using agents to try to add types. It's harder to get real numbers on how that's worked because it's not all monitored in a way. So what we have are at scale, we've given a number of tasks to agents and looked at like the success rates when they're able to autonomously drive it. And if the problem is reasonably scoped, we get about 70%.
Thank you. Appreciate it.